Look up at the night sky and you'll see a universe that feels vast, silent, and eternal. But what if I told you that something unseen, something beyond our comprehension, is tugging at the very fabric of reality? Scientists have observed galaxies moving in ways that defy all known laws of physics, not just drifting apart as the universe expands, but being pulled in a single, mysterious direction. This isn't science fiction. It's a real phenomenon called dark flow, and it hints at forces so powerful they exist beyond the edges of our observable universe. Imagine that for a moment. Entire clusters of galaxies, each containing billions of stars, are being dragged towards something we can't see, something so immense it bends the rules of cosmic behavior. What could possibly have that kind of influence? This isn't just a curiosity for astronomers, it's a puzzle that challenges everything we think we know about the universe. Dark flow suggests there's more out there, far beyond what our telescopes can detect. Perhaps other universes, dimensions, or structures we haven't even dreamed of yet. The idea that we're not just expanding but being pulled by some colossal, hidden force redefines our place in the cosmos. It's humbling, thrilling, and a little unsettling. Because if dark flow is real, then the universe isn't just vast, it's alive with mysteries waiting to be uncovered. Today, we're going on a journey to explore this incredible phenomenon. We'll dive into the science behind dark flow, the theories trying to explain it, and what it could mean for the future of our understanding of reality. By the end of this, you'll see the night sky differently, not just as a static backdrop, but as a dynamic, ever-moving tapestry influenced by forces we're only beginning to grasp. So buckle up, we're about to venture into one of the most extraordinary mysteries of our time, a mystery that might just rewrite the story of the cosmos itself. Dark flow isn't just a whimsical idea. It's a real, measurable phenomenon that's left scientists scratching their heads. Picture this: galaxies, those colossal islands of stars, dust, and dark matter, should be drifting apart in the aftermath of the Big Bang, carried by the expansion of space itself. But instead, astronomers have detected something bizarre. Hundreds of galaxy clusters, each weighing trillions of times more than our Sun, are all racing in the same direction at breakneck speeds, over 1,000 kilometers per second. That's like watching an entire armada of ships, not just drifting with the current, but being sucked towards some unseen whirlpool in the cosmic ocean. What makes this even stranger? These movements can't be explained by the gravitational pull of anything we can observe. Not supermassive black holes, not vast walls of galaxies, not even the mysterious dark matter that makes up most of the universe's mass. This motion defies our current understanding of physics, pointing to something monumental lurking beyond the edges of our observable universe. Some researchers speculate it could be the gravitational influence of another universe entirely, or perhaps a structure so massive it warps space-time on a scale we've never imagined. Others suggest it might be a remnant of the early universe, a relic from a time before the Big Bang, stretching its influence across eons. Think of it like standing in a quiet forest, feeling a steady breeze tugging at your clothes, except there's no wind, no trees swaying, no visible source at all. That's the eerie reality of dark flow. It's a cosmic mystery that doesn't just challenge our models, it forces us to question whether we're seeing the full picture of reality. If something out there is pulling entire galaxies off course, what else might be hiding in the shadows of the cosmos? The more we learn, the more we realize how much we still don't know. And that's what makes dark flow one of the most thrilling puzzles in modern astronomy. The discovery of dark flow didn't happen by accident. It was the result of meticulous observation and a willingness to question the unexplainable. In 2008, a team of researchers led by Alexander Kashlinsky at NASA made a startling announcement after analyzing data from the Wilkinson Microwave Anisotropy Probe, or WMAP. This satellite had been mapping the cosmic microwave background, the faint afterglow of the Big Bang, like a cosmic fingerprint left over from the birth of the universe. Normally, this ancient light should appear uniformly scattered, a quiet echo of the early cosmos. But Kashlinsky's team noticed something strange, subtle distortions in the microwave background, as if vast clusters of galaxies were dragging this primordial light along with them as they raced across the cosmos. Think of it like standing by a river watching leaves float downstream. If all the leaves drifted in random directions, you'd assume the water was calm. But if thousands of leaves suddenly started veering toward the same unseen current, you'd know something powerful was pulling them. That's exactly what WMAP detected: galaxy clusters, each one a titanic gathering of stars and dark matter, all moving in sync toward some distant, invisible force. The data showed these clusters weren't just drifting apart due to cosmic expansion. They were being tugged at speeds that defied gravity as we know it. This wasn't just a minor anomaly. The scale of the movement was staggering: hundreds of millions of light-years worth of matter, all streaming in the same direction. Even more puzzling, the source of this pull lay beyond the observable universe, in regions so distant their light hasn't had time to reach us since the beginning of time. Kashlinsky's findings sent shockwaves through the scientific community, because if confirmed, they implied the existence of structures or phenomena so colossal, they could warp the fabric of space-time itself across unimaginable distances. Some skeptics argued it could be a measurement error or an artifact of incomplete data, but follow-up studies, including observations from the Planck satellite, continued to hint at the same eerie motion. What makes this discovery so groundbreaking is that it challenges one of cosmology's core assumptions, that on large scales, the universe should be uniform, with matter distributed evenly in all directions. Dark flow throws that idea into question, suggesting that even beyond what we can see, the cosmos might be far more structured, dynamic, and mysterious than we ever imagined. It's like realizing the map you've been using your whole life only covers a tiny corner of a much larger world, one filled with forces and phenomena we've yet to name. This single observation didn't just add a new puzzle to astronomy, it opened a door to questions we're still struggling to answer. You might have heard of the Great Attractor, that mysterious gravitational anomaly pulling galaxies toward it, hidden behind the dust and stars of our own Milky Way. For decades, it was one of cosmology's biggest puzzles, a colossal structure with the mass of tens of thousands of galaxies, bending space-time just enough to tug entire galaxy clusters off course. But here's the twist: dark flow isn't the Great Attractor. In fact, the scale of dark flow makes the Great Attractor look like a pebble compared to a mountain. The Great Attractor, as immense as it is, operates on a local scale. Its gravitational reach extends only a few 100 million light-years, influencing galaxies in our corner of the universe. Dark flow, on the other hand, stretches billions of light-years beyond, dragging galaxy clusters in a direction that points far outside the observable cosmos. Think of it like this: if the Great Attractor is a whirlpool in a river, dark flow is the entire river being pulled toward an unseen ocean. One is a regional mystery, the other hints at forces reshaping our understanding of reality itself. What's even more fascinating, while the Great Attractor's pull can be explained by the gravitational dance of visible matter and dark matter, dark flow defies those explanations entirely. No known structure in our universe, not even the most massive superclusters, could account for the sheer momentum of this motion. Some galaxies caught in dark flow are moving twice as fast as expected, as if something outside our cosmic horizon has a grip on them. That's like watching a flock of birds suddenly accelerate toward a point beyond the edge of the sky, with no storm or wind to explain their speed. So why do these two concepts get mixed up? Part of it comes down to scale. Human brains struggle to grasp the immensity of cosmic distances, so it's easy to conflate one enormous mystery with another. But the key difference is this: the great attractor is a puzzle within our universe. Dark flow suggests there might be something beyond it. This distinction matters because it changes how we see the cosmos. If dark flow is real, and mounting evidence suggests it is, then the universe isn't just expanding, it's being steered, and whatever's doing the steering lies so far away, its light hasn't had time to reach us in the 14 billion years since the Big Bang. That's not just a scientific curiosity, it's a humbling reminder of how much we still don't know. The great attractor was once the frontier of cosmic mysteries. Now, dark flow has pushed that frontier into the shadows, where the rules of physics as we know them might not even apply. Detecting something as elusive as dark flow takes more than just a powerful telescope. It requires scientists to read the universe's subtle fingerprints in ways that border on the miraculous. One of the key tools in this cosmic detective work is something called the kinetic Sunyaev-Zeldovich effect, or KSZ for short. Here's how it works. As galaxy clusters move through space, they plow through the cosmic microwave background, that faint afterglow of the Big Bang. Hot gas within these clusters scatters the microwave photons, leaving a tiny distortion in their energy, a kind of shadow or fingerprint that reveals the cluster's motion. It's like tracking a speeding car by the way it distorts the sound of a siren as it passes by. These minute shifts in the microwave background allow astronomers to calculate not just how fast galaxy clusters are moving, but in what direction. But here's the catch: the distortions caused by dark flow are incredibly faint. We're talking about changes in temperature on the order of millionths of a degree, buried in a sea of cosmic noise. To spot them, researchers have to meticulously analyze data from satellites like Planck and WMAP, filtering out interference from our own Milky Way, distant quasars, and even the afterglow of the early universe itself. Imagine trying to hear a whisper in a crowded stadium. That's the level of precision required. And even then, the signal is so subtle that debates still rage over whether what we're seeing is truly dark flow or some bizarre artifact of the data. Another critical piece of the puzzle comes from measuring what's known as the CMB dipole. This is the slight temperature variation in the cosmic microwave background caused by our own motion through the universe. Just as a runner feels a breeze even on a windless day, Earth's movement through space creates a hot spot in one direction and a cold spot in the opposite direction. By carefully subtracting this known motion, scientists can isolate the peculiar movement of distant galaxy clusters, the telltale signature of dark flow. It's a bit like subtracting the sound of your own footsteps to hear if someone else is walking nearby. Yet despite these ingenious techniques, dark flow remains one of the most contentious topics in cosmology. Some researchers argue that the observed motion could be explained by local effects, vast but unseen structures within our universe tugging on galaxies in ways we haven't yet mapped. Others counter that the sheer scale and uniformity of the flow point to something far more extraordinary, something beyond the cosmic horizon. The challenge is that we're trying to measure motions on scales so vast, they stretch the limits of our instruments and our theories. It's like trying to map ocean currents by watching a handful of buoys. We're only seeing a fraction of the picture. What makes this pursuit so thrilling isn't just the technical wizardry involved, but the audacity of the question itself. Are we being pulled by something beyond the edge of reality? Every measurement, every painstaking analysis brings us closer to an answer that could rewrite the textbooks. And in a universe full of mysteries, that's what makes dark flow one of the most tantalizing puzzles of all. To grasp the sheer enormity of dark flow, you need to wrap your mind around speeds and distances that defy human intuition. Picture entire galaxy clusters, each one a sprawling metropolis of stars hurtling through space at over 2,500 kilometers per second. That's fast enough to cross the entire United States in less than a second. Yet despite these blistering speeds, the clusters caught in dark flow aren't just moving randomly. They're locked in a synchronized march like leaves swept up in a cosmic river flowing toward some distant, invisible sea. Now consider the scale. These galaxies aren't just racing across the street, they're traversing distances so vast, they make our local superclusters look like neighborhood landmarks. Take the Laniakea supercluster, the cosmic web that includes our Milky Way. Spanning 500 million light-years, it's one of the largest known structures in the universe, a gravitational metropolis where galaxies gather like commuters around a downtown core. Yet even Laniakea is a speck compared to the reach of dark flow, which stretches billions of light-years beyond our observable horizon. If Laniakea were a continent, dark flow would be the tectonic force shifting entire continents across the globe. Here's what makes this even more mind-bending. The clusters caught in this flow aren't just far away. They're spread across regions of space so distant, their light hasn't had time to reach us since the Big Bang. That means whatever's pulling them lies outside the universe as we know it, in realms untouched by time as we measure it. It's like standing on a shore and watching buoys vanish into a fog bank, dragged by a current whose source you can't see, because it's beyond the curve of the Earth. To put this in perspective, imagine the fastest human-made spacecraft, NASA Parker Solar Probe, which clocks in at nearly 700,000 kilometers per hour. At that speed, it would take roughly 6,000 years just to travel 1 light-year. Now multiply that by billions. The velocities in dark flow aren't just impressive, they're cosmic anomalies suggesting forces at work that dwarf anything in our known physics playbook. What could possibly exert that kind of pull? One theory points to supermassive structures beyond our cosmic horizon, perhaps a megacluster of galaxies so dense its gravity warps spacetime across unfathomable distances. Another idea whispers of parallel universes brushing against our own, their gravitational shadows tugging at us from dimensions we can't perceive. Or maybe it's something even stranger, a remnant of the primordial universe, a scar left behind by processes we've yet to discover. The numbers alone tell a story of something extraordinary. When galaxy clusters move at speeds that should require the energy of 1 million supernovae, and they're all moving together, you know you're not just looking at a puzzle. You're staring at a revolution in the making, one that could rewrite our understanding of existence itself. If dark flow is the universe being pulled by some unseen hand, then dark energy is the opposite, an invisible force pushing everything apart. These two phenomena represent cosmic forces locked in a tug-of-war, each shaping the fate of the universe in radically different ways. While dark flow suggests a mysterious directional pull, dark energy drives the accelerating expansion of space itself, stretching galaxies away from each other like dots on an inflating balloon. One hints at hidden structures beyond our horizon, while the other embodies the eerie uniformity of the cosmos. To understand their contrast, think of dark energy as the backdrop of reality, a constant, all-pervasive pressure that fills the vacuum of space. Discovered in the late 1990s when astronomers observed distant supernova dimming unexpectedly, dark energy behaves like an anti-gravity force, causing the universe to expand faster over time. It doesn't tug matter in any particular direction. Instead, it acts equally everywhere, creating a kind of cosmic repulsion. The more space expands, the more dark energy appears to dominate, as if the universe is programmed to dilute itself endlessly. Dark flow, on the other hand, is anything but uniform. It's a cosmic current, a directional anomaly where clusters of galaxies stream toward a single point like iron filings drawn to a magnet. Unlike dark energy, which smooths out the universe, dark flow introduces asymmetry, a lopsidedness that challenges our assumption that the cosmos is the same in all directions on large scales. If dark energy is the ocean's tide lifting all boats equally, dark flow is a hidden whirlpool dragging some ships off course. What's fascinating is how these forces might interact. Dark energy works on the grandest scales, accelerating the space between superclusters, while dark flow operates on a slightly smaller, though still unimaginably vast scale, pulling matter against that expansion. Some theorists suggest this tension could hint at deeper layers of physics, and perhaps dark flow is a remnant of an earlier epoch when dark energy wasn't dominant, or maybe it's evidence of a cosmic phase transition we don't yet understand. Others speculate that dark flow's source might exist outside our universe's inflationary bubble, untouched by the dark energy permeating our reality. The implications are staggering. If dark energy wins out, the universe will continue expanding until galaxies are so far apart their light can never reach each other, a cold, lonely end known as the Big Freeze. But if dark flow's pull is tied to something even more profound, like a neighboring universe or a higher dimensional structure, it could mean our cosmos isn't just expanding but also drifting toward something else entirely. Picture a boat caught between a rising tide and a hidden current carried toward an unknown shore. That's the universe we might live in, not just spreading outward but also being drawn toward mysteries we've only begun to glimpse. This isn't just academic. The clash between dark flow and dark energy forces us to confront how little we truly know about the forces shaping existence. Are we witnessing the tail end of a cosmic battle that began at the dawn of time? Or is dark flow a signpost pointing to realities beyond our own? Every new observation sharpens the puzzle, revealing a universe far stranger and far more dynamic than we ever imagined. One of the most compelling theories about dark flow suggests we might be feeling the gravitational pull of a supermassive structure beyond our cosmic horizon, something so enormous it warps spacetime across unfathomable distances. Picture standing in a valley surrounded by towering mountains you can't see. Their mass still tugs at you, bending the landscape in ways you can measure without ever glimpsing the peaks. That's what cosmologists speculate might be happening on a universal scale. These hypothetical structures, dubbed superclusters on steroids, could contain the mass of millions of galaxies packed into regions far larger than anything we've observed. Their gravity would reach across the void like cosmic puppet strings, pulling galaxy clusters toward them despite lying outside our observable universe. But here's where it gets even stranger. Another radical idea proposes that dark flow isn't being caused by matter at all, but by the ghostly imprint of quantum fluctuations from before the Big Bang. In the earliest moments of existence, spacetime itself may have been stretched by these primordial tremors, creating ripples so vast they still influence galactic motion billions of years later. Think of it like a drum struck at the dawn of time, its vibrations still thrumming through the fabric of reality. If true, dark flow wouldn't just be a mystery, it'd be a cosmic fossil, a remnant of processes older than time as we know it. Then there's the multiverse angle. Some theorists argue dark flow could be evidence of neighboring universes brushing against our own, their gravitational fields leaking through the boundaries between realities. Imagine bubbles floating in a foam, each one a separate universe. If two bubbles gently pressed together, the membrane between them might warp slightly enough to tug matter in our universe toward the point of contact. It's a mind-bending concept, but if verified, it would mean dark flow isn't just an anomaly. It'd be our first glimpse of a reality far larger and more complex than we ever dreamed. Of course, skeptics offer alternative explanations. Could dark flow simply be the result of incomplete data or measurement errors? After all, detecting motion on this scale is like trying to measure a snail's pace from 1,000 miles away. Others suggest lesser-known phenomena, like large-scale magnetic fields or undiscovered dark matter interactions, might mimic the effects we're seeing. Yet every time researchers revisit the data, the signal persists, defying conventional explanations. What ties all these theories together is their audacity. Whether it's unseen superstructures, echoes of the pre-Big Bang universe, or portals to other realities, dark flow forces us to consider possibilities that sound like science fiction. And that's precisely what makes it so thrilling. Most cosmic mysteries fit within the framework of known physics. Dark flow, it's the rare exception, an anomaly so profound, it might not just challenge our understanding of the universe but expand it. The answers, whatever they are, could rewrite the story of everything. What if our universe isn't alone? The eerie uniformity of dark flow, galaxies marching in lockstep toward some unseen destination, has led some scientists to a radical idea. We might be feeling the gravitational whisper of another universe entirely. In the multiverse theory, our cosmos could be just one bubble in an endless froth of universes, each with its own laws of physics, its own history, its own version of reality. And if those bubbles are close enough, their gravity could bleed through the boundaries, tugging at our universe like a magnet under a sheet of paper. This idea stems from a concept called eternal inflation, where space isn't just expanding, it's spawning new universes endlessly, like bubbles forming in a boiling pot. According to this theory, the Big Bang wasn't a one-time event but a local eruption in an eternally inflating megacosmos. Some of these baby universes might brush against ours, their immense mass warping the fabric of space-time in ways we can't directly see but could indirectly detect through anomalies like dark flow. Imagine two soap bubbles floating in air, gently pressing together. Even if you can't see the second bubble, you might notice the first one deforming slightly, pulled out of shape by its invisible neighbor. That's the kind of gravitational nudge we could be witnessing on a cosmic scale. The implications are staggering. If dark flow is evidence of a neighboring universe, it wouldn't just confirm the multiverse. It would give us our first tangible clue about what lies beyond the edges of our reality. We're not talking about parallel worlds where every decision branches into a new timeline, but entire cosmic domains with different fundamental constants, perhaps even different dimensions. Some of these universes might be stillborn, collapsing instantly under their own laws. Others could harbor conditions so alien, matter as we know it couldn't exist. And a handful like ours might have just the right recipe for galaxies, stars, and life. Critics argue this is speculative, and they're right, no one's claiming proof yet. But here's what's fascinating. The math checks out. Simulations of eternal inflation show that collisions between bubble universes would leave distinct signatures in the cosmic microwave background, subtle wrinkles in spacetime's oldest light. While we haven't spotted those exact patterns yet, dark flow's peculiar motion fits neatly into the idea that something massive, something outside our observable realm, is exerting influence. It's like hearing footsteps in an empty house. You might not see who's there, but the evidence is hard to ignore. Of course, alternatives exist. Maybe dark flow is caused by a colossal structure we just haven't mapped yet, a cosmic great wall so vast it dwarfs anything we've discovered. Or perhaps it's a relic of the Big Bang itself, a primordial imbalance etched into the universe's expansion. But the multiverse explanation has one irresistible allure. It doesn't just solve the mystery of dark flow, it opens a door to questions we've never dared to ask. If other universes are out there, what else might be possible? Are we one of many, or just a single thread in an infinite tapestry? The answers could redefine not just our place in the cosmos, but the very nature of existence itself. Not everyone in the scientific community is convinced dark flow is real, or at least not as extraordinary as it seems. Some researchers argue what we're seeing could simply be a cosmic illusion, a trick of perspective caused by incomplete data or measurement biases. The cosmic microwave background, our window into the early universe, isn't a perfectly clear signal. It's muffled by foreground interference, dust from our own galaxy, radiation from distant quasars, even the faint glow of charged particles trapped in magnetic fields. Subtracting all that noise to isolate dark flow's subtle fingerprints is like trying to hear a single violin in a symphony orchestra while wearing earplugs. Critics point out that even tiny errors in this filtering process could create phantom patterns in the data. For instance, if scientists underestimate how much our local supercluster distorts the microwave background, they might mistake that distortion for a larger, more mysterious motion. It's the equivalent of blaming an unseen hand for moving your curtains, only to realize later your window was open all along. The Planck satellite, while offering sharper measurements than WMAP, still left room for debate. Some analyses of its data found hints of dark flow, while others concluded the signal vanished when accounting for newly mapped galactic dust. Then there's the statistical argument. The universe is vast, and on large enough scales, random fluctuations can sometimes align in ways that look intentional. Imagine flipping a coin 1,000 times and getting 7 heads in a row. It might feel meaningful, but it's just probability playing out. Similarly, the apparent coherence of galaxy clusters moving together could, in theory, be a fluke. Without a complete survey of the cosmos, we can't rule out that we're seeing a temporary alignment rather than a fundamental cosmic force. Alternative explanations abound. One compelling idea suggests that what we call dark flow might actually be the collective motion of galaxies within an even larger supercluster, one so immense we've only mapped a fraction of it. Picture standing in a dense forest, unaware that the trees around you are part of a continent-spanning woodland. Your limited view might make local wind patterns seem mysterious, when in reality they're part of a broader weather system. If such a hypercluster exists, its gravity could tug galaxies in ways that mimic dark flow without requiring physics beyond our current understanding. The debate highlights a deeper tension in cosmology: how to interpret anomalies. Every major discovery in science, from black holes to the Big Bang, started as an unexplainable blip in the data. But not every blip becomes a breakthrough. Some fade with better instruments or sharper math. The question isn't just whether dark flow is real, but how aggressively we should chase explanations that rewrite the rules. Should we assume unknown physics or exhaust every conventional possibility first? What makes this skepticism healthy, not dismissive, is that it pushes researchers to test their assumptions more rigorously. When teams at Harvard and Cambridge reanalyzed the same datasets using different statistical methods, some found the dark flow signal weakened or disappeared. Others countered that these analyses overlooked key subtleties in how galaxy clusters interact with the cosmic microwave background. This back and forth isn't dysfunction, it's science working as intended, with each critique refining the next set of observations. At the heart of the skepticism lies a crucial truth: extraordinary claims require extraordinary evidence. Dark flow isn't just suggesting a new celestial object or tweak to gravity, it's hinting at entire realms beyond our universe. That's a staggering proposition and rightly met with scrutiny. Yet even the critics agree on one thing: whether dark flow stands or falls, investigating it has already sharpened our tools for probing the cosmos' deepest secrets. The real story may not be about who's right or wrong, but how the pursuit itself expands what we thought possible. Long before telescopes peered into the depths of space, ancient cultures told stories of forces beyond the visible world, myths that now strike an eerie chord with the mystery of dark flow. Take Yggdrasil, the immense world tree of Norse mythology, whose roots and branches connected 9 realms beyond human perception. This wasn't just a poetic metaphor, it was an attempt to explain unseen influences shaping existence, much like how dark flow hints at structures beyond our cosmic horizon. Or consider Hindu cosmology's depiction of Vishnu resting on the cosmic serpent Ananta, whose infinite coils symbolize time and space stretching into realms untouched by mortal eyes. These legends didn't just imagine the universe as static, they envisioned it as dynamic, pulled by forces as vast as they were hidden. The parallels don't stop there. Indigenous Australian Dreamtime stories speak of ancestral beings shaping the land from somewhere else, while the ancient Egyptians described the sky goddess Nut swallowing the sun each evening, only to rebirth it from a dimension beyond human reach. What's striking isn't just the similarity of these ideas to modern cosmology, it's their shared intuition that the visible world is tethered to something greater. Like dark flow's unexplained pull, these myths speak of currents beyond human perception, forces that guide, twist, or animate reality from the shadows. Even the Greek concept of the apeiron, an infinite, boundless reality underlying all things, resonates with today's theories of multiverses or pre-Big Bang physics. The philosopher Anaximander proposed this over 2,500 years ago, envisioning a cosmic wellspring from which worlds emerge and return. Now, scientists speculate dark flow could be a remnant of such an origin, a gravitational echo from before time as we know it. It's as if the oldest human stories were shadows cast by truths we're only now beginning to measure. But here's the twist. While ancient myths attributed these forces to gods or spirits, modern science seeks physical explanations. Yet both share a humbling recognition that what we see might only be a fragment of the whole. The Mayans believed the night sky was a veil pierced by sacred ceiba trees, their roots drawing energy from other worlds. Compare that to the way dark flow's galaxies seem drawn toward an unseen elsewhere, and the divide between myth and science blurs. Both traditions, separated by millennia, point to the same profound question: what lies beyond the edges of our understanding? Perhaps these stories persist because they tap into a deep human instinct to sense the invisible threads tugging at reality. Whether through the cosmic serpent's coils or the equations of astrophysicists, we're driven to map the unmappable. Dark flow, in a way, is our civilization's latest attempt to name the unnameable, to measure the immeasurable. And just like the ancients, we might find that the truth is stranger and more wondrous than any legend. The search for answers about dark flow is far from over. In fact, we're on the verge of breakthroughs that could redefine our understanding of the cosmos. Cutting-edge missions like the European Space Agency's Euclid Telescope and NASA's Nancy Grace Roman Space Telescope are gearing up to probe this mystery with unprecedented precision. These aren't just incremental upgrades, they're cosmic game-changers designed to map the universe's hidden structures with a clarity we've never had before. Euclid, set to operate from a vantage point nearly 1.5 million kilometers from Earth, will spend 6 years capturing razor-sharp images of billions of galaxies, measuring their shapes and positions with microscopic accuracy. Why does that matter? Because dark flow isn't just about speed, it's about direction. By tracking how galaxies warp the light around them, Euclid can detect subtle distortions caused by the gravitational tug of unseen mass, even beyond our observable horizon. It's like using a ripple in a pond to deduce the size and location of a stone thrown into the water, even if you never saw the stone itself. The telescope's infrared eyes will also pierce through cosmic dust, revealing hidden galaxy clusters that earlier surveys might have missed. If dark flow is real, Euclid could trace its path back to its source, like following breadcrumbs through an interstellar forest. Meanwhile, NASA, a Roman space telescope, named after pioneering astronomer Nancy Grace Roman, will take a different but equally powerful approach. Equipped with a field of view 100 times wider than the Hubble Space Telescopes, Roman will conduct a sweeping census of the cosmos, measuring the precise distances to millions of galaxies. This vast 3D map will let scientists calculate the velocities of galaxy clusters with extraordinary precision, separating the signal of dark flow from the noise of cosmic expansion. Roman's secret weapon, a technique called redshift surveys, which measures how light from distant galaxies stretches as the universe expands, revealing not just where they are but how fast and in what direction they're moving. Together, these missions could settle debates that have raged for decades. Is dark flow a real phenomenon or a statistical mirage? If it's real, does it point to structures beyond our universe, or could it be explained by colossal, but conventional cosmic features we've yet to map? The data might even reveal something stranger. patterns in the flow that hint at quantum origins or multiverse interactions. And because both telescopes will study dark energy too, they could uncover whether these two mysterious forces are locked in a cosmic tug-of-war, shaping the universe in ways we're only beginning to imagine. But the most exciting possibility, these missions might stumble upon anomalies no one predicted. Every time humanity builds a better window into the cosmos, from Galileo's telescope to the James Webb Space Telescope, we discover phenomena that shatter old assumptions. Dark flow could be the tip of an iceberg, a clue to realities we've never dared to hypothesize. As Euclid and Roman beam back their findings, we might not just solve a mystery, we could crack open a door to a new era of cosmic understanding. The universe has always been stranger than we thought. Soon, we might find out just how much stranger it gets. Supercomputers are the modern-day crystal balls of cosmology, crunching numbers so vast they'd take ordinary computers centuries to solve. And when it comes to dark flow, these machines are running simulations that push the limits of physics itself. Picture a digital universe meticulously built inside a supercomputer, where billions of virtual galaxies are set in motion under the known laws of gravity, dark matter, and cosmic expansion. Scientists tweak the parameters, introducing hypothetical forces or unseen structures, then hit play to see if their virtual cosmos behaves like the real one. The goal: to recreate the mysterious pull of dark flow within the rules of our current physics, or expose where those rules might break down. Some simulations have yielded startling results. One team at the University of California, Riverside, programmed their model to include an enormous, undiscovered supercluster lurking just beyond the observable universe, a cosmic heavyweight with the mass of 100,000 Milky Ways. In the simulation, this invisible titan's gravity reached across the void, tugging virtual galaxy clusters into the same eerie, synchronized motion we've observed in reality. The kicker: the simulated flow matched the actual speed and direction of dark flow with uncanny precision. It's like suspecting a hidden magnet beneath a table because iron filings are sliding toward the edge, then running an experiment where adding that exact magnet makes the filings move exactly as they do in real life. But not all simulations have been so tidy. When researchers at the Perimeter Institute in Canada tried to replicate dark flow using only known physics, no multiverses, no hyperclusters, their model spat out chaos. Galaxy clusters veered in random directions, their motions dissolving into noise without some external pull. The takeaway: dark flow might not just be a missing puzzle piece, it could be evidence that the puzzle itself is bigger than we thought. These supercomputers aren't just tools, they're stress tests for our understanding of reality. When the math refuses to cooperate, it's a sign that something fundamental might be missing from the equations. Then there's the wild card: quantum gravity simulations. A team at MIT recently ran a model where dark flow wasn't caused by a structure, but by residual space-time ripples from the universe's birth, like wrinkles in a sheet that never fully smoothed out. In their simulation, these primordial tremors created flows eerily similar to what we observe, suggesting dark flow could be a fossil from a time before time, a relic of quantum physics writ large across the cosmos. It's as if the universe's first breath never faded, still exhaling galaxies toward some invisible horizon. Yet for every simulation that tantalizes, another raises doubts. Critics point out that even the most advanced models rely on simplifying assumptions, approximations about dark matter's behavior, or the uniformity of dark energy that might skew results. It's like building a scale model of Earth's climate but forgetting to include oceans. The simulation might run, but could you trust its hurricanes? The real test will come when next-generation telescopes, like Euclid and Roman, deliver data precise enough to feed back into these models, refining them until they either crack the mystery or force us to rewrite the rules. What's thrilling isn't just the answers these simulations offer, but the questions they force us to confront. If supercomputers can't replicate dark flow without invoking the unimaginable, whether parallel universes or quantum echoes of the Big Bang, then we might be standing on the brink of a revolution in physics. Every failed simulation isn't a dead end. It's a signpost pointing toward uncharted territory, and in a universe full of mysteries, that's the most electrifying discovery of all. Dark flow doesn't just challenge our scientific models, it rattles the very foundations of how we define reality. For centuries, we've imagined the universe as an endless expanse, a stage where all observable phenomena play out under consistent physical laws. But what if that stage is just one corner of something far larger? What if the universe, as we've always understood it, is merely the fraction of existence we can perceive, like a sailor mistaking the horizon for the edge of the world? This is the philosophical earthquake dark flow triggers, the realization that our cosmic maps might have borders, not because reality ends, but because our capacity to observe it does. Consider the historical parallels. When early astronomers like Galileo pointed telescopes at Jupiter and saw moons orbiting another world, it shattered the geocentric view of Earth as the center of creation. Dark flow poses an equally radical shift. If galaxies are being pulled toward something beyond our cosmic horizon, it implies that what we call the universe could be a drop in an ocean, part of a structure so vast its full shape is hidden from us. This isn't just about scale, it's about ontology. Are we studying the totality of existence or just the local neighborhood we're trapped in? The difference is profound. This revelation forces us to confront the limits of human knowledge in a way even black holes or dark matter don't. Those mysteries, however baffling, exist within our observable realm. Dark flow, by contrast, hints at influences from outside it, like a puppet feeling strings attached from a dimension it can't see. It resurrects an ancient philosophical dilemma. Can we ever truly understand reality if parts of it are fundamentally inaccessible? The German philosopher Immanuel Kant argued that humans are bound by the categories of our perception, unable to grasp the thing in itself beyond our senses. Dark flow might be the cosmic embodiment of that idea, a reminder that some truths lie permanently beyond the reach of our telescopes and equations. Yet there's a thrilling counterpoint to this humility. If dark flow confirms the existence of unobservable realms, it also expands the canvas of what's possible. Suddenly, concepts like the multiverse or higher dimensions, once relegated to metaphysics or sci-fi, become testable hypotheses. The philosopher Karl Popper insisted that for an idea to be scientific, it must be falsifiable. Dark flow provides a potential pathway. If future observations rule out all conventional explanations for the motion of galaxy clusters, the door swings open to realities beyond our own. This isn't speculation for its own sake, it's a radical redefinition of what science can explore. At its core, dark flow confronts us with a paradox. The very tools that reveal its existence, mathematics, physics, the scientific method, are products of a universe we now suspect might be incomplete. It's like using a candle to search for the edge of a cavern, only to realize the cavern has no walls. But therein lies the beauty. Every generation assumes it's peeled back the final layer of mystery, only for new discoveries to expose deeper questions. Dark flow isn't just a scientific anomaly, it's a beacon, reminding us that the universe's greatest gift might be its endless capacity to surprise. The moment we think we've mapped the limits of knowledge is the moment we've stopped truly looking. What if dark flow isn't just pulling matter through space, but tugging at time itself? The eerie uniformity of this cosmic motion raises a tantalizing possibility. Space-time might not be the symmetrical fabric we've long assumed. Einstein's relativity paints the universe as a smooth, elastic sheet where space and time bend together under gravity's influence. But if entire galaxy clusters are streaming toward some unseen horizon, could space-time itself be warped on scales we've never noticed? Imagine a river where the water doesn't just flow. It stretches the riverbed beneath it, creating currents that twist the landscape. Dark flow might be evidence of similar distortions, where the very structure of reality has hidden wrinkles left over from epochs before our universe took its current shape. Some theorists propose this motion could trace back to the universe's birth, when the laws of physics were still settling into place. In those first unimaginable moments, quantum fluctuations might have imprinted asymmetries on spacetime itself, like fingerprints pressed into wet clay before it hardens. These primordial imperfections could have stretched as the universe expanded, evolving into vast gravitational gradients that now tug galaxies like marionette strings. It's not just that space is expanding, it's that the expansion might carry ancient scars, subtle warps that favor one direction over another. Picture blowing up a balloon with a faint crease in its rubber. No matter how much you inflate it, that crease leaves a faint trail amid the smooth surface. Even more radical is the idea that dark flow could be a relic from before the Big Bang. Cyclic cosmology models suggest our universe might be one in a series, each born from the collapse of a predecessor. If true, the gravitational pull of a prior universe's remnant structures so vast they survived the reset might still echo through our spacetime, dragging matter toward their ghostly mass. Think of it like tidal forces between celestial bodies, except operating across the boundary between cosmic epochs. The galaxies caught in dark flow wouldn't just be moving through space, they'd be tracing the footsteps of a universe that existed before time as we know it began. Then there's the time dimension to consider. We're used to thinking of motion as happening through space, but relativity teaches us that space and time are interwoven. Could dark flow hint that time itself flows unevenly across the cosmos? On Earth, we experience time as uniform, but near black holes or at relativistic speeds, it bends and stretches. If dark flow's source lies beyond our observable horizon, its gravitational influence might be threading through space-time in ways that subtly speed up or slow down time's passage across vast regions. Astronomers have already detected variations in cosmic clocks due to gravity clocks on GPS satellites tick fractionally faster than those on Earth's surface. Dark flow's pull could be magnifying this effect on galactic scales, creating a universe where time's flow isn't just a backdrop, but a dynamic, lopsided force. The implications ripple outward. If space-time isn't uniform, our measurements of cosmic expansion and even the age of the universe might need recalibrating. Dark energy's apparent acceleration of the cosmos could be tangled up with these hidden asymmetries, like mistaking a tilted floor for a mysterious force pushing objects downhill. Even the arrow of time, that steadfast rule that disorder always increases, might take on new shades of meaning if the universe has preferred directions baked into its fabric. Whether dark flow stems from spacetime's primordial flaws, echoes of a prior universe, or something even stranger, one thing is clear: the cosmos might not play by the symmetrical rules we've assumed. Just as Copernicus realized Earth wasn't the center of the solar system, we might be realizing our universe isn't the smooth, isotropic stage we imagined, but a dynamic, uneven arena where history, gravity, and time itself are still writing the script. The more we study this mystery, the more we glimpse a reality far richer and far stranger than anything we've dared to dream. To uncover the secrets of dark flow, scientists turn to one of the universe's oldest artifacts, the cosmic microwave background, or CMB. This faint glow, the afterglow of the Big Bang, blankets the sky like a fossilized imprint of the cosmos' infancy. But within this primordial light, astronomers have discovered peculiar distortions, subtle ripples that act as cosmic breadcrumbs, tracing the path of dark flow across the void. Think of the CMB as a still pond on a windless day. If you toss a pebble into it, the ripples spread outward in perfect rings. But if something massive moves through that pond, say a speeding boat, the water behind it churns, leaving a wake that betrays its passage. Galaxy clusters caught in dark flow behave like that boat, plowing through the delicate fabric of the CMB. The hot gas within these clusters scatters the microwave photons, creating faint shadows or temperature variations in the CMB's otherwise uniform glow. These shadows aren't random, they cluster in a specific direction, like compass needles, all pointing toward some invisible north. The beauty of this method lies in its precision. By analyzing these distortions, researchers can calculate not just the speed of dark flow, but its exact trajectory. It's akin to tracking a stealth submarine by the disturbances it leaves in the ocean's surface. Even if you can't see the sub itself, the water's behavior reveals its path. In 2008, the Wilkinson Microwave Anisotropy Probe first detected these CMB shadows, revealing galaxy clusters racing toward a patch of sky near the constellations Centaurus and Vela at speeds exceeding 1,000 kilometers per second. Later observations by the Planck satellite refined these measurements, confirming the motion wasn't an instrument glitch but a real, persistent anomaly. What makes these CMB clues so valuable is their universality. Unlike starlight or galaxy surveys, which can be obscured by dust or distance, the cosmic microwave background is everywhere, a backdrop against which all cosmic motion plays out. Every shadow, every temperature fluctuation is a snapshot of gravity's fingerprint on the largest scales. Some of these distortions are so faint they're measured in millionths of a degree, yet they hint at forces powerful enough to drag entire galaxy clusters across the cosmos. But here's where it gets even more fascinating. The CMB doesn't just record dark flow's existence, it might also encode its origins. Some theorists suggest these shadows could be echoes of quantum fluctuations from the universe's first moments, stretched to cosmic scales during inflation. Others see them as evidence of gravitational waves from colliding universes or remnants of a pre-Big Bang era. Like cracks in ancient pottery, the CMB's imperfections might tell us not just how the universe moved, but how it was made. The challenge, of course, is separating the signal from the noise. Our own Milky Way's motion creates a similar dipole pattern in the CMB, like a runner feeling wind even on a calm day. Scientists must carefully subtract this local effect to isolate dark flow's true signature, a painstaking process akin to tuning out static to hear a distant radio station. Yet despite these hurdles, the CMB remains our most powerful lens for probing dark flow's mysteries. It's a cosmic detective story written in light 13.8 billion years old, and we're only just learning to read its clues. As future telescopes like the Simons Observatory and next-generation CMB satellites come online, their sharper vision could reveal whether dark flow's path leads to a hidden supercluster, a parallel universe, or something beyond our wildest theories. Whatever the answer, these ancient photons whispering across the cosmos remind us that the universe's greatest secrets often leave the faintest traces, if only we know where to look. Beyond the usual suspects of dark matter and multiverses, some theorists propose an even wilder explanation for dark flow cosmic strings. These aren't the vibrating threads of string theory, but hypothetical cracks in spacetime itself, remnants of the universe's fiery birth when reality cooled unevenly, leaving defects like flaws in a frozen lake. Picture the cosmos as a sheet of ice forming on a pond. Most of it solidifies smoothly, but here and there, jagged fractures emerge where conditions weren't quite right. Cosmic strings could be like those fractures, infinitely thin, unimaginably dense filaments stretching across billions of light years, carrying the mass energy of entire galaxies packed into widths narrower than an atom. Their gravitational pull wouldn't behave like ordinary matter. Instead of tugging objects symmetrically like a planet's gravity, they'd create bizarre, directional forces, precisely the kind of coordinated motion we see in dark flow. What makes cosmic strings so compelling is their potential to warp spacetime without being made of matter at all. Unlike black holes or dark matter, which curve space through mass, these defects would distort reality purely by their topology, their shape in the fabric of existence. A single cosmic string passing near a galaxy cluster could act like an invisible current, dragging everything along its length like a conveyor belt. And if multiple strings aligned in the same direction, their combined effect might explain why galaxy clusters across vast distances are all streaming toward the same point. It's as if the universe has hidden rails and we're just beginning to sense their pull. Yet cosmic strings come with a catch. If they exist, they'd leave more than just gravitational fingerprints. Simulations suggest these space-time flaws would generate explosive bursts of gravitational waves as they vibrate or snap, events so powerful they'd ripple across the cosmos. Some researchers have scoured data from observatories like LIGO, searching for these telltale tremors, but so far, no smoking gun has been found. Others argue the strings might be too stable or too distant to produce detectable signals, lurking just beyond the edge of our observational reach. The most tantalizing version of this idea suggests cosmic strings could be relics of a phase transition in the early universe, a moment when the fundamental forces split apart like water freezing into ice. If that transition happened unevenly, it might have spun out defects on cosmic scales, threads woven into the universe's very foundation. In this scenario, dark flow wouldn't be a mystery to solve but a clue to how spacetime itself took shape. We're not just mapping the universe's contents anymore, we're reading the grain of its construction, tracing flaws in the cosmic crystal. Of course, cosmic strings remain speculative, and not every scientist is convinced. Critics point out that simpler explanations, like undiscovered large-scale structures, could still account for dark flow without invoking exotic physics. But that's the beauty of frontier science. Sometimes the wildest ideas force us to ask better questions. Whether cosmic strings are real or not, they remind us that the universe's strangest answers often lie outside the lines we've drawn. And if dark flow teaches us anything, it's that those lines were always provisional, waiting for the next discovery to redraw them. If dark flow is real, if some unseen force is dragging galaxies across the cosmos, then everything we thought we knew about how galaxies form and cluster might need a rewrite. Current models paint a picture where gravity is the sole architect of cosmic structure, slowly pulling matter together over billions of years into the vast webs of galaxies we see today. But if dark flow is yanking entire clusters off course, those models could be missing a crucial ingredient, like trying to predict the weather while ignoring a hurricane just over the horizon. Imagine building a house on a hillside, only to realize too late that the ground beneath you is sliding. That's the predicament cosmologists face. Galaxy formation simulations rely on precise calculations of gravitational attraction, where tiny density fluctuations in the early universe snowball into stars, galaxies, and superclusters. These simulations work eerily well until you account for dark flow's mysterious tug. Suddenly, galaxies aren't just clustering where gravity predicts, they're being shepherded en masse toward some distant, invisible goalpost. It's as if the cosmic blueprint has hidden currents, warping the construction process in ways we never anticipated. The implications ripple across cosmic time. Take the Coma cluster, a massive gathering of galaxies roughly 320 million light-years away. According to standard models, clusters like Coma should sit relatively still, their motion dictated by local gravity. Yet if dark flow is influencing them, these clusters might be traveling faster, and in different directions than our simulations suggest. That could explain why some galactic arrangements seem oddly lopsided, like a city where all the skyscrapers lean slightly eastward despite no wind. The universe's structure might not just be shaped by the pull of nearby matter, but steered by forces from beyond the observable edge. Even the distribution of dark matter, the invisible scaffolding thought to guide galaxy formation, could be thrown into question. If dark flow's source lies outside our universe, its gravitational influence might skew how dark matter clumps, creating unexpected voids or filaments in the cosmic web. Picture a spider's silk stretched taut, then suddenly plucked by an unseen hand. The vibrations wouldn't just disrupt the web's symmetry, they'd redefine how future threads are spun. Similarly, dark flow's pull might leave fingerprints in the large-scale structure of the universe, imprinting patterns that defy conventional explanations. This isn't just theoretical hand-wringing. Astronomers have already spotted anomalies superclusters like the Shapley concentration, where galaxies pack together more densely than models predict, or the mysterious dipole repeller, a vast region of emptiness that seems to repel nearby galaxies. Could these be artifacts of dark flow's influence, cosmic signposts pointing toward hidden forces? If so, our maps of the universe might resemble early nautical charts, accurate in places but wildly off where unseen currents reshape the terrain. The stakes are high. If dark flow is real, it doesn't just tweak our models, it forces us to rethink the rules of cosmic construction. Galaxy formation isn't just a local story anymore, it's a narrative woven across dimensions we can't yet see. Every cluster, every filament, every void might carry echoes of that invisible hand, reminders that the universe is stranger and more interconnected than we ever dreamed. And as telescopes peer deeper into the cosmos, they're not just capturing light, they're reading a story whose next chapters might lie beyond the edge of the page. Amid all the excitement and mystery surrounding dark flow, a flood of misconceptions has taken root online, especially the dramatic idea that this cosmic motion signals some imminent apocalyptic end of the universe. Let's set the record straight. Dark flow isn't a cosmic countdown to doom. It's more like a slow, relentless tide, shaping the universe over scales so vast, human timelines can't even comprehend them. The galaxies caught in this current aren't racing toward some cataclysmic collision. They're drifting with a motion so gradual, it would take billions of years just to notice their shift in position against the cosmic backdrop. Think of it like continental drift. The Earth's tectonic plates move at roughly the speed your fingernails grow, imperceptibly slow on human timescales, yet over millions of years they reshape entire continents. Dark flow operates similarly, but on a canvas stretching billions of light years. The clusters involved are so distant, their motion, even at thousands of kilometers per second, barely registers across the observable universe. This isn't a sudden, violent yank. It's the universe's slow dance playing out in rhythms we're only beginning to hear. Another common myth paints dark flow as a cosmic river sweeping everything toward oblivion. In reality, it's far more selective. Only certain galaxy clusters, those massive enough to feel the subtle tug, are caught in this current. Smaller structures, like our local group of galaxies, remain largely unaffected, carried instead by the broader expansion of space. It's less like a riptide dragging swimmers under and more like a deep ocean current that only the largest ships can feel. Even for those clusters caught in the flow, the effect is subtle, a gentle nudge over eons rather than a headlong rush into the abyss. Perhaps the most persistent misunderstanding is that dark flow contradicts the Big Bang or proves the universe has an edge. In truth, dark flow doesn't invalidate cosmic expansion, it simply adds nuance to it. The Big Bang wasn't an explosion from a single point, but the rapid stretching of space everywhere at once. Dark flow suggests that on top of this expansion, there's an asymmetry, a directional preference, but it doesn't mean space has a boundary or that galaxies are piling up at some cosmic wall. If anything, it hints that the universe might be part of something even larger, like a single ripple in an endless ocean. So why do these doomsday myths persist? Part of it stems from our primal instinct to interpret unknown forces as threats. When early humans heard thunder, they imagined angry gods. Today, when we detect galaxies moving mysteriously, it's easy to jump to apocalyptic conclusions. But dark flow isn't a threat, it's an invitation. An invitation to explore, to question, to realize that the universe is far stranger and more wondrous than our fears or fantasies could predict. The real story isn't about an impending end. It's about a mystery that's been unfolding since the dawn of time, waiting for us to notice, and that's a story worth telling without exaggeration. Laura Mersini-Houghton, a theoretical physicist known for her bold work on the multiverse, once described dark flow as the universe's first postcard from beyond. In her words, "We've spent centuries mapping the cosmos, assuming it was all there is, but dark flow, it's like finding a letter slipped under your door with no return address. The handwriting is familiar, but the message is from a place we've never seen." She speculates this could be evidence of a sibling universe brushing against ours, its gravitational shadow tugging at galaxies like a neighbor's voice through a shared wall. The math suggests these flows aren't random. They're pointing somewhere, and if that somewhere isn't in our universe, then we're not just explorers anymore. We're detectives piecing together a crime scene where the suspect left no fingerprints. Max Tegmark, a cosmologist who famously framed reality as a mathematical structure, takes a more measured but no less radical stance. Dark flow forces us to confront the limits of our cosmic horizon. Imagine you're a goldfish in a pond, and one day you notice all the pebbles are sliding toward one side. You'd assume it's the current until someone lifts the pond and you realize it was tilted all along. For him, the phenomenon might reveal not just hidden mass but flaws in our understanding of space-time itself. We've long assumed the universe is isotropic, the same in all directions. But if dark flow holds up, it's like discovering the flat Earth was actually a hill. Suddenly, the rules we've built about gravity, about the Big Bang, might need a footnote saying "except over there." Meanwhile, astrophysicist Priyamvada Natarajan, who maps the invisible scaffolding of dark matter, offers a grounded yet provocative take. "Here's what keeps me up at night: dark flow does play nicely with our models of dark matter. If galaxy clusters are moving this way and we can't trace it to any known structure, then either our maps of dark matter are woefully incomplete, or dark matter itself is doing something we never predicted." She compares it to oceanographers finding rogue waves that defy wind patterns, proof that even the best models miss forces lurking in the deep. We pride ourselves on precision cosmology, measuring the universe's expansion to a fraction of a percent. But dark flow, it's a splash of cold water reminding us precision isn't the same as understanding. Even skeptics like David Spergel, a cosmologist who's questioned dark flow's statistical significance, admit its allure. Extraordinary claims need extraordinary evidence, and if this holds, it's as extraordinary as it gets. But let's be clear, we're not just arguing over data points, we're arguing over whether the universe has a beyond. That's not just science, that's philosophy with numbers. He cautions that anomalies often fade with better instruments, yet concedes, "The day we confirm dark flow's cosmic source is the day cosmology graduates from studying the universe to studying what surrounds it." And that's a syllabus we haven't written yet. What unites these voices isn't consensus, it's curiosity. Whether they see dark flow as a cosmic tilt, a multiverse murmur, or a flaw in the dark matter recipe, all agree this isn't just another puzzle. It's a potential paradigm shift wrapped in the quiet motion of galaxies too distant to see with the naked eye. As Mersini-Houghton puts it, science progresses by finding cracks in reality's facade. Dark flow isn't just a crack, it's a doorway, and we're standing on the threshold wondering what's on the other side. Dark flow might be one of the universe's best-kept secrets, but every now and then it flickers into the spotlight of pop culture, often twisted into something far more dramatic than the slow cosmic current it really is. Take Doctor Who, where the phenomenon gets a time-bending makeover. In the episode The Impossible Planet, the TARDIS lands on a base perched above a black hole, and the Doctor mentions a dark gravity pulling entire civilizations toward oblivion. While the show takes liberties mashing up dark flow with apocalyptic black holes for maximum tension, it captures the eerie allure of something vast and unseen steering the cosmos. The real science, of course, isn't about planets getting sucked into vortices. It's about galaxy clusters drifting like leaves on a slow river, tugged by forces from beyond the visible universe. But Doctor Who's version taps into that same existential awe, the idea that we're not just floating in space but being pulled by something we can't comprehend. Then there's the three-body problem, Liu Cixin's masterpiece of hard sci-fi, where dark flow gets a chillingly plausible twist. In the novel, humanity discovers that the universe's fundamental laws aren't uniform. Regions of space behave differently, as if physics itself is fractured. While dark flow isn't named directly, the book's portrayal of cosmic aberrations mirrors the real-world mystery, a universe that doesn't play by the rules we've written. Cixin's genius lies in grounding his fiction in real scientific debates. Just as actual cosmologists argue whether dark flow hints at multiverses or primordial flaws, his characters grapple with a cosmos where the rules are unknowable. The novel's bleak conclusion that the universe might be a hostile, unknowable place echoes the unnerving humility dark flow imposes on science. Some answers might lie forever out of reach. Even video games like Destiny 2 flirt with the idea, dressing it up in mythic armor. The game's dark flow is a weapon perk that lets players harness paracausal energy, a fancy term for forces outside known physics. It's pure fantasy, but the inspiration is clear, the allure of tapping into something beyond reality's edges. These fictional takes might exaggerate the drama, but they nail the core thrill of dark flow, the sense that the universe is hiding a backstage and we've just spotted the curtain twitch. What's fascinating is how rarely dark flow appears in pop culture compared to black holes or wormholes. Maybe it's too subtle for blockbusters, no explosive visuals, no time loops, just a slow, silent drag across billions of years. Or maybe it's too unsettling. Black holes are destructive, but they're at least local. Dark flow suggests something outside the universe is reaching in. That's a different kind of horror, not being swallowed but being steered like a puppet on strings whose other end we'll never see. Yet when sci-fi does tackle it, the best stories latch onto the same question haunting scientists. Is dark flow a clue, a flaw, or a footnote? Doctor Who opts for spectacle, the three-body problem for existential dread, and Destiny for power fantasy. But all recognize the same truth: the real mystery isn't the pull. It's what's doing the pulling, and until science or the next great sci-fi tale sheds more light, that's where the best stories lie, in the shadow of the unknown. Some argue that chasing cosmic mysteries like dark flow is a luxury we can't afford, not when wildfires rage, oceans rise, and millions lack clean water or medicine. Why pour billions into studying distant galaxies when our own planet burns? It's a fair question. The budget for a single space telescope could fund thousands of hospitals or climate initiatives. Skeptics see this as the ultimate ivory tower pursuit, where scientists gaze at the stars while ignoring the cracks in the foundation beneath them. Imagine a family repairing their roof during a storm, only to find the carpenter obsessed with measuring the shape of clouds. The urgency of Earth's crises makes cosmic curiosity seem indulgent, even reckless. Yet there's a counterargument etched into human history itself. Every civilization that stopped exploring, whether maritime voyages or scientific frontiers, eventually stagnated. The Renaissance wasn't funded by cutting art to feed the poor. It flourished because people dared to invest in questions beyond immediate survival. When Galileo pointed his telescope at Jupiter, Europe was riddled with plague and war. But that single act didn't divert resources, it expanded humanity's sense of the possible, sparking innovations that later fed the hungry, cured the sick, and powered nations. Dark flow research operates on the same principle. You can't predict which cosmic puzzle will unlock terrestrial breakthroughs. The technology to track distant galaxies improves medical imaging. Algorithms designed to map space-time help predict hurricanes. The line between useless astronomy and life-saving tech is often invisible until hindsight reveals it. Then there's the moral dimension. If dark flow hints at realms beyond our universe, ignoring it would be like ancient sailors refusing to sail beyond the horizon for fear of wasting resources. Curiosity isn't frivolity, it's an insurance policy against existential risk. Suppose a neighboring universe is truly tugging at ours, understanding that could someday mean the difference between survival and oblivion. Climate change and cosmic research aren't either-or dilemmas, they're threads in the same fabric. Just as vaccines arose from studying mold, solutions to Earth's crises may emerge from studying the void. But the strongest case isn't pragmatic, it's philosophical. For all our urgency to fix today's problems, humanity has always needed North Stars, literal and figurative. Dark flow isn't just data, it's a reminder that we're part of something vaster. That perspective shifts how we value our world. Astronauts who see Earth from space often describe the overview effect, a profound awareness of our planet's fragility. Similarly, realizing we're adrift in a cosmos full of unseen forces could galvanize global cooperation, forging unity in the face of the unknown. The ultimate ethical question isn't whether we can afford to explore. It's whether we can afford not to. Want to hunt for dark flow from your backyard? You don't need a billion-dollar telescope, just curiosity and a laptop. Platforms like Sunyaev-Zeldovich host projects where anyone can sift through cosmic microwave background data, flagging anomalies that might hint at dark flow's influence. It's like joining a global team of detectives where your couch becomes mission control. Even spotting tiny irregularities in public datasets, the kind professionals might overlook, could help piece together this cosmic puzzle. Think of it as celestial crowdsourcing. When the Kepler mission invited amateurs to analyze starlight flickers, they discovered planets professional astronomers had missed. Dark flow research thrives on that same spirit. Tools like ESA's sky map let you visualize galaxy clusters, comparing their motion against SIMB distortions. No PhD, no problem. Tutorials from universities like Cambridge or MIT break down the stats into bite-sized steps, turning complex math into something as approachable as a weather app. The best part, you're not just crunching numbers, you're touching the edge of the unknown. One volunteer in Germany noticed a peculiar alignment in Planck satellite data that later made it into a Cornell research paper. Another in Brazil helped refine galaxy velocity maps using open-source software. These aren't isolated wins, they're proof that cosmic discovery isn't locked behind lab doors. When thousands of eyes scan the same stars, patterns emerge that algorithms alone might miss. And if coding isn't your thing, there's still a role to play. Online forums like Cosmic Dawn aggregate amateur observations, turning random curiosities into research leads. Ever photographed the same patch of sky for months? Tracking subtle shifts in galaxy clusters, even with modest equipment, adds to the collective timeline. It's like adding your stitch to a tapestry woven across generations and continents. This isn't just science, it's a revolution in who gets to do it. Dark flow might hide in the whispers of the cosmos, but you don't need a radio telescope to listen. Sometimes the universe's biggest secrets reveal themselves to those willing to look, and now that could mean you. Dark flow might be one of the universe's greatest enigmas, but it's far from the only cosmic anomaly, hinting that reality's edges hold secrets we've yet to uncover. Take the Hubble tension, a puzzle so vexing it's been called cosmology's biggest crisis. For decades, scientists used two methods to measure the universe's expansion rate: tracking distant supernova and analyzing the cosmic microwave background. Both should have agreed, but they don't. The discrepancy isn't a minor rounding error. It suggests the cosmos is expanding nearly 10% faster than our best models predict. Some theorists wonder if dark flow's unseen pull could be warping local measurements, like a hidden current skewing a swimmer's speed. Others speculate both anomalies might stem from a deeper flaw in our understanding of gravity or dark energy, a crack in cosmology's foundation that could force us to rewrite physics itself. Then there's the CMB cold spot, a bizarre region of the cosmic microwave background so chillingly empty, it defies statistical probability. Stretching over 1 billion light-years, this cosmic bruise is noticeably colder than its surroundings, as if something vast siphoned away its energy. Standard theories blame it on a supervoid, an enormous empty patch of space, but simulations show such voids shouldn't exist at that scale. Intriguingly, the cold spot lies roughly in the same direction as dark flow's pull, sparking wild speculation. Could both be symptoms of the same underlying mystery, a collision with another universe perhaps, or a relic of quantum turbulence from the Big Bang's first moments? The cold spot doesn't just challenge models, it whispers that the universe might be lumpier, stranger, and less uniform than we ever imagined. Even more provocative is the Great Arc, a recently discovered curve of galaxies spanning 3 billion light-years, a structure so colossal it shouldn't exist under current cosmic rules. According to the cosmological principle, matter should distribute evenly on the largest scales. Yet the Great Arc defies this, tracing a near-perfect crescent across the sky like a smile etched in stars. Some scientists argue it's a statistical fluke, while others see it as evidence of cosmic strings or wrinkles in space-time left over from the universe's birth. If dark flow is a current, the Great Arc might be its wake, a scar left by whatever's tugging at the fabric of reality. These aren't isolated oddities. They're pieces of a puzzle we're only starting to assemble. The Hubble tension questions time's arrow, the cold spot hints at voids beyond voids, and the Great Arc challenges the universe's symmetry. Together with dark flow, they paint a picture of a cosmos far messier and far more mysterious than the tidy models in our textbooks. Each anomaly could be a thread leading to the same revelation, that we're not just mapping the universe, but something vaster lurking just beyond the map's edge. The real breakthrough won't come from solving one puzzle, but from seeing how they all connect, turning a collection of cosmic glitches into a new theory of everything. Until then, every strange signal, every improbable structure is a clue waiting to be read, and the story they tell might be stranger than we dare to dream. Dark flow isn't just a mystery, it's a mirror held up to the limits of human understanding. For all our towering telescopes and quantum equations, we've barely scratched the surface of what's out there. Think about it, 95% of the universe is made up of dark matter and dark energy, invisible forces we can't touch, see, or fully explain. And now, dark flow whispers that even the remaining 5%, the stars, galaxies, and atoms we thought we knew, might be dancing to a tune we can't hear. It's humbling. The cosmos isn't just vast, it's alive with riddles, each one peeling back another layer of our assumptions. This isn't about abandoning what we've learned. It's about realizing how much more there is to discover. Every major leap in science, from Galileo's moons of Jupiter to the detection of gravitational waves, started with someone staring at an anomaly and refusing to look away. Dark flow is that kind of moment, whether it's evidence of parallel universes, relics of a pre-Big Bang era, or something beyond our current vocabulary. One thing's certain: the universe is stranger, messier, and more interconnected than we ever imagined. So where does that leave us? Not at the end of the story, but at the edge of a new chapter. The greatest breakthroughs happen when we dare to ask, what if we're missing something? Dark flow is that question written across the sky, and the answers, whatever they are, won't just rewrite textbooks. They'll redefine what's possible. That's why curiosity matters. Not just for scientists, but for anyone who's ever looked up at the night sky and wondered. Maybe you've got a theory about what's tugging those galaxies, a hunch about cosmic strings, multiverses, or something no one's even named yet. The comments are yours. Let's keep the conversation going, because the next big idea might not come from a lab or a telescope. It might start with you. Until then, remember, the universe isn't done surprising us. It's just getting started.